So yesterday, sorry, the 5 of you, class recording has started, so just don't do anything stupid, all right? Because the number of possibilities for who did the stupid thing is greatly reduced now. So, all right. So yesterday we talked about energy transfer, and we talked about that there are 3 ways to do it. Okay. So the towards the end of class, I kind of gave you guys. We'll not even go that route, so we'll just go back here. So, okay. So first, we talked about conduction. We said that conduction is when we're transferring energy by direct contact. So conduction relies on contact, right? That the particles of a substance have to be touching each other in order for energy transfer to occur by conduction, right? And we said that if that would be something like if we're talking about passing one thing to another, okay? The example that I use in class sometimes would be, so let's say, we have a full class, not this class, but we have a full class, and I know this is kind of like old school, right? Maybe you've seen it in a movie or something, but let's say you have to pass a note from one side of the room to the other side of the room, okay? I know all of you are pretty note-passing kind of guys, so this would make a lot of sense, but maybe it's a little note that says, hey, do you like me? Check one box, yes, no, something like that, right? That note is the energy, right? That's the ability to cause change, right? That could send you down a path to true love and whatever it might be, so, but that's the energy, right? The note is playing the role of the energy. So we have to get it from one side of the room to the other side of the room, okay? So conduction, right? Conduction would be that note starts on one side, you pass it to the person next to you, right? Then that person passes it to the person next to them, then that person passes it to the person next to them, and that person passes it to the person next to them, right? Transfer of energy with no transfer of matter. So the note has moved, but nobody has gone anywhere, right? That's the idea of conduction. And if, like in this room, there's a big break between 2 desks, right, where there is no matter and there's no contact, right, conduction's going to stop. And we talked a little bit about that yesterday, like with the thermos and the vacuum layer and the thermos and stuff like that. Okay? Right? Conduction occurs fastest in solids, right? And slowest in gases, just because of the sheer spaces that are in between those particles, right? It depends on contact. The more they contact, the faster the conduction happens. So, I think that was one of the questions there, right? It says, what does it say there? I should pull up the actual. So it says, right? Use the pictures to explain why conduction occurs more slowly in gases than it does in solids and liquids. Because, like we said, conduction depends on contact, and there's going to be more frequent contact between the particles in a solid than there is going to be in a liquid or a gas, just because of how close they are. All right? Good there? All right. The next, let's go here. Just because conduction happens the fastest in a solid does not necessarily mean that all solids are good conductors. In some solids, the particles may be close together, but because they're held so tightly in place, like this picture here, it shows these lines in between the particles are supposed to represent like vibration of the particles, right? That they vibrate a little bit in place. But in certain materials, because those particles are held in, because of the way that they're put together and some of the attractions between them, even they don't vibrate a whole lot. And if they don't vibrate a whole lot, they don't conduct very well. So just because conduction happens fastest in a solid doesn't necessarily mean that it happens well in all solids. And that gives us in the difference between a thermal conductor and a thermal insulator. So a thermal conductor is a material that conducts thermal energy well. These are things that you might think of like that, as you probably can name a few. Metals are good conductors, right? Certain metals are better conductors than other metals. That's why we make things that you cook in out of metal, right? Because we want to transfer that heat quickly from the burner into the food that we're trying to cook. Floor tiles are generally good conductors. You get that sensation in the morning if you're walking through the hallway and like you have carpet in your hallway, and then as soon as you step in the bathroom, right, it feels cold, right? Like the floor of the bathroom feels cold. It's not because the tiles in the bathroom are any better or any colder than the carpet. It's just that the tiles conduct heat better. So heat flows out of your foot faster than it does in the carpet, and it makes your foot feel colder. Not necessarily that those tiles are any colder than the carpet in the hallway. Okay. Thermoconductors usually have low specific heat values. We have not introduced the concept of specific heat. We'll do that today, and that's part of our discussion for today. So you make a note of that. On the other hand, thermal insulators, material that conducts thermal energy poorly. You could probably name a few of those, right? Those are the things that we use like for handles and like oven mitts and stuff like that, right? Wood, plastic, styrofoam, right? A big wool sweater. Thermal insulators usually have high specific heat values. Like I said, we'll introduce that concept of specific heat as we get further. All right, it's good there? Next type of energy transfer is convection. And we talked about that convection involves the transfer of a warm fluid. So something has to move to carry that heat. So going back to our example of passing the note from one side of the room to the other, right? This would be like if you have the note in your hand and you real sort of sly-like stand up and walk towards the garbage can, but on the way to the garbage can, you just happen to pass by the person who you're trying to send the note to's desk, right? So you kind of walk casual and just sort of like drop it off real casual on the way by, and then you pretend like you threw something out in the garbage can, right? The note ended up getting moved from one side of the room to the other. But in that case, something actually took it there, right? There was actually a movement of matter. And that's the whole idea of convection, where we have something that's moving in order to transfer that energy, right? That fan over there, that fan is there because it's conducting, right? Or sorry, not conducting, it's convecting. I'm trying to move the warm air around the room to try and get it nice and evened out instead of all of it staying right where it comes out of the vents, all right? That's what I'm trying to do with the fan over there. Or we kind of talked yesterday about when you blow on your hot food. Did we talk about that in class, or was that the other class? Can't remember. Right. Did we talk about that? Right. So if your food is hot, right, the first thing you do is you blow on it, right, to cool it down. Because your food is hot, it's going to make the air around it hot. But if you blow on it, you move that hot air away from the food and you replace it with cooler air. And that then causes more heat to flow out of that food and into the air around it, and that causes it to cool down a little bit faster. Convection is responsible for something that we call a convection current. A convection current is the rationale behind hot air rising and cool air sinking. But that's not really what it is. Convection current is also the...
Good morning, everyone. Again, pardon the interruption. I'm going to be calling two more groups out to assembly at this point.
Right. Convection current is also the same thing that's responsible, like we talked a couple days ago about the lava lamp, yes? Did we talk about the lava lamp in here? Oh my God. Are we all familiar with a lava lamp? Yes, okay. So, a lava lamp, right? you got the clear liquid, and then you got like the little red liquid that sits down in the bottom, right? It doesn't have to be red, it can be any color, but, and so you turn the lava lamp on, and it causes that stuff in the bottom to heat up. But when things get hot, generally what happens to their volume? We can talk, there's only 5 of us, so go ahead. When things get hot, what generally happens to their volume?
Expands.
They expand, right? And if things expand, what happens to their density?
Decreases.
It decreases, right? Where do less dense things go? Up, right? So you heat up the stuff that's at the bottom of the lava lamp, it expands, it becomes less dense, it rises. But as it rises, right, what happens to its temperature?
Cools down.
Cools down. If it cools down, its volume decreases, right? And that makes its density increase. So where does it head?
Down.
Back down, right? We call that a convection current. It's moving energy around in a substance because it alternately rises and cools, and that affects the density of a substance, okay? It's not that hot air rises, it's more that hot air is actually what?
Less dense.
Less dense, and that causes it to rise, but then when it rises, it becomes cooler, and it becomes more dense, and it falls back down. Okay? So hot air doesn't rise because it's hot, it rises because it's less dense generally than the cooler air. Perhaps you've seen this if you drink coffee or if your parents drink coffee, right? If they have a hot cup of coffee and they put the little cream in it, the cool cream that goes in it, you can see it kind of like mixes itself almost. That's a convection current that's setting up stuff. Back in 7th grade or 8th grade, when you guys did the little earth science stuff, convection currents are also responsible for what process on Earth?
Tectonic plate movement.
Plate tectonics, right? That the hot magma comes up from the core, right? And it comes out and it cools down and it keeps those plates moving, right? All right, good there? Okay. Last one we talked about yesterday, radiation. Transfer of energy by waves through space. If we go back to our analogy of passing a note in class, right? What does radiation look like? You make a paper airplane, you throw it across the room, right? That's romantic, a paper airplane. It's like, so, okay. But in that case, right, the energy, the note that you're trying to pass, goes from one side to the other side. Nothing took it there, but would it matter if there was anybody in these seats? Does the paper airplane need people to be in the seats between you and the person you're passing the note to? Nope, it can go straight there. So we can transfer energy by waves through space. We don't have to have matter in that place in order to carry the energy from one place to the other. All objects are going to radiate energy. It's just how fast do they do it, and that depends on the temperature. Okay. This energy transfer is a key part of the study of thermodynamics, right? If it's thermo, that means it's going to deal with what? Temperature, heat, right? And if it's dynamic, that means that it does what? It changes, right? So we're dealing with changes in heat, the study of the conversion between heat and other forms of energy. So that study of thermodynamics leads us to engines and how do we transfer that energy efficiently from one form to another form. The study of thermodynamics is based on 3 laws that we call the 3 laws of thermodynamics, which I suppose is appropriate. So, first, energy is conserved. That includes thermal energy. Not earth-shattering there, right? We've talked about that on several occasions. That idea of conservation and what that means, keeping things the same, even though it may transfer from one form to another form, right? The total amount is going to be conserved. 2, earlier in this unit we talked about the idea that energy flows from hot things to cold things spontaneously. We can get the opposite to happen. But we have to add energy to that system. Energy won't flow from cold to hot spontaneously. You have to make it happen. Just like this ball, right? Spontaneously, which way does it go? Which way is it going to go on its own? It's going to go down, right? Because that's less energy, right? Less potential energy. Will it go up?
Yes.
If it's forced to, right? Not on its own, but I can make it go up, right? If I do work on it, if I add energy. Same thing, right? We can get energy to flow from hot things to cold, or sorry, from cold things to hot things if we do work. That's the basis of pretty much how your refrigerator works. So, and then the last thing, we talked briefly about the idea of absolute zero. Absolute zero is theoretically the lowest temperature that we can reach. If we go back to the beginning of this unit, right, what does temperature tell us? Movement, right? So there is a theoretical temperature where all movement stops. But how do we get things colder? Go ahead.
Decreasing the movement of the particles.
Yes, how does that happen?
You put it next to something colder.
You have to put it in contact with something colder, right? Because hot things flow from hot to cold, okay? If absolute zero is the coldest temperature theoretically, we can't get there, right? Because in order to make something colder, you put it in contact with something colder than itself. But if that's the lowest, right, there isn't, negative absolute zero, right? A theoretical idea, but in reality, we can't get there. We get close, but in reality, we can't get to that point where all movement stops because energy has to be conserved. So if you make something colder, something else is going to get warmer. And you can't make anything get to zero because there's nothing below zero. Does that make sense? Good there? Okay. So we talked about the idea that solids transfer energy the fastest, right? They conduct energy the fastest. But I also kind of mentioned to you the idea that just because solids conduct energy the fastest doesn't necessarily mean that all solids conduct electricity. Electricity, heat. But I also kind of in this part here mentioned the idea of specific heat values. So that is where we are going next. All right. So we have talked about the idea of energy moving from one place to another because of a temperature difference, and we call that energy heat that flows from one place to another. Temperature measures how much those particles move. How much energy actually moves we call heat. Well, how much energy is that? How much energy will flow from a hot thing to a cold thing? It depends on a couple of factors. One big factor that it depends on is called the specific heat of a substance. By definition, the specific heat of a substance is the amount of energy needed to raise the temperature of 1 gram of a material by 1 degree Celsius. So the amount of energy needed to raise the temperature of 1 gram of a material by 1 degree Celsius. So we're dealing with an amount of energy in order to change the temperature of a substance. All substances don't change their temperature at the same rate. The lower its material's specific heat value, the more the temperature will rise if a given amount of energy is absorbed. It is easier to change the temperature of a substance that has a low specific heat. specific heat values means the temperature is going to change faster. That applies when we're both heating something up or cooling it down. All right, for instance, so you get a pot of water, you put it on your stove, you turn the stove on, okay? And you let the pot of water sit there for 1 minute on top of the stove, okay? 1 minute. After 1 minute, can you stick your hand in the water that's in the pot? After 1 minute on the stove? Probably, yeah, right? Doesn't heat up all that much in 1 minute, right? But should you pick the pot up and touch the bottom of the pot that the water is sitting in? Probably shouldn't do that, right? Why? Because those materials have different specific heat values. They've been exposed to the same amount of energy, but one has gotten hot very quickly and the other one has not, right? It's easier to speed up the movement of the particles in some things, like metals, than it is in other things, like water. Okay? How quickly do those particles move? It depends on forces of attraction a lot. Okay? So a couple of examples. First, okay? This is a little bit of a dramatization, but, right? Have you ever, you go to McDonald's and you get the little dessert pie that's at McDonald's? Yes? No? Man. Let me think of something. Kyle, you ever have pizza bites after school? Okay, so pizza bites, right? You put them in the microwave, blah, 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 you know, take them out, cool them down, stuff like that, pick it up, oh, it's good to go. You bite in the pizza bite and what happens? You burn the inside of your mouth, right? Because the outside was all good to touch, right? Inside, not so much, okay? Right? Different specific heat values, right? The outside of the crust of this pie, or the pizza bite in that case, right, has a lower specific heat value than the stuff on the inside of the pizza bite, right? It's easier to heat things up or cool things down that have a lower specific heat value. Case of if you ever get one of those McDonald's pies before, right? There's a warning right on the box, right? It says warning: filling may be hot, right? Not that they keep those things scalding or anything like that, but right? But you know, if you have like or if you've ever eaten just like a piece of pizza before, right? You pick that bad boy up and it's all good to pick up and you bite it, right? But the sauce is still like scaldingly hot, you know, right? Because different specific heat values. Okay. Another example. Are we good with that? Another example. Not that this has been like, you know, on the front of everybody's mind lately, but if you go to the beach in the summer, right, it'll happen. Really, it'll warm up eventually. So you go to the beach in the summer, right? And you're kind of sitting there on the beach towel, you know, in the middle of the beach, and everything's good with you sitting on the beach towel, but as soon as you step onto the sand, right, what happens? Feet get burned, right? So where do you go? You head to the water, right? Water's okay to touch, right? Has the water been exposed to any less sunlight than the beach has? They've both been in the sun the same amount of time, but the beach is scaldingly hot and the water isn't. Why? Because the sand has a lower specific heat value. It's easier to heat up the sand than it is to heat up the water. The water has a high specific heat value. It's harder to heat it up than it is to heat the sand up.
value, then
Yes.
why does the filling of the pie have a larger one?
What's the filling of the pie mostly made out of?
Filling?
Well, let's say it's fruit. Let's say it's fruit pie, right? What's fruit mostly made out of?
Water?
Water, right? But the crust of the pie is made out of like flour.
Why does the filling stay hotter?
Because if it's mostly water, right, that means it has a high specific heat value. It's harder to change its temperature, okay? Eris, have you ever made a pie before or seen anybody bake a pie before?
No.
Okay. A lot of times when people bake a pie, anybody can vouch for this, okay? Especially like a fruit pie, like an apple pie that's like really big, okay? You have to cook that pie for an hour-ish or so, okay? Depends on how big it is and stuff like that, okay? Eris, have you ever made biscuits in the oven before?
Yeah.
Okay. Biscuits take how long to cook?
I don't know.
15 minutes, something like that. So you got to cook the biscuits 15 minutes, but you got to cook the pie an hour, right? Now, size differences obviously have something to do with that, but a lot of the cooking time of the pie isn't the crust, it's the filling. Because the filling has a high specific heat because it has a lot of water in it, right? It takes longer to heat that water up than it does to heat the crust up. Does that make sense?
So why wouldn't the crust be hotter?
It's the same temperature when they come out of the oven, okay? But things that have high specific heat values are hard to heat up, or slow to heat up, I guess we should say, but they're also slow to cool down, okay? Because it's how hard or easy, or how strongly does it hold the energy, right? So it's harder to heat up, or it's slower to heat up, but it's also slower to cool down, okay? Example, and this kind of leads to the next thing here, right? In November or December, okay? A lot of times we will have snow that falls over the land, right? But if you go to the lake, right, is the lake frozen yet?
No.
No. Why? Because, or let's say, let's not go snow. Let's say we might have a really cold day in December, right? It might be 20 degrees in December, right? But if you go to the lake, has the lake frozen yet?
No.
No, because it's been heating up all summer. So it takes a long time for it to heat up, but it also takes a long time to cool down. So even though it may be very cold in December, the lake is still not at that freezing point of water because it's still releasing that energy very slowly. Does that make sense?
Yeah.
Okay. It's in reverse in the springtime though. We may have a day that's 65. It's supposed to be 50 degrees today, right? But if you go to the lake, it's still going to be frozen, right? Because it takes a lot longer to heat that water up than it does to heat up, the ground and the grass and the trees and stuff like that, okay? It's one of the reasons why that if you go, you'll get to experience this in the spring, right? If you go to Avon Lake or Bay for a spring sport, okay, you guys will get to experience this year if you haven't experienced it in middle school, right? It's always freezing at Avon Lake or Bay in the spring because both of those schools are like a block off of the lake. And it might be 60 degrees here, but if you go just like a mile or two north, it's a lot colder because that water is still very cold by the lake because it hasn't had a chance to heat up yet. Does that make sense?
Yeah.
Okay. So, the last little thing there, right? Water is king when it comes to specific heat capacity. That means water has a very high specific heat capacity, meaning that it's hard to get it to heat up, but it's also hard to get it to cool down. water has a very high specific heat value. And that means it's hard to get it to heat up, but it's also hard to get it to cool down. Okay. Next, how much energy are we actually gaining or losing, and then what does that do to the temperature of that substance? Like I said, if you go to the beach, right? If you go to the beach in the summertime, the sand gets really, really hot, the water not so much. They've both been in the sun the same amount of time. They both get the same amount of energy, but the temperature change is not the same. And that has to deal with this equation. Q equals M times C times delta T. All right? So, Q stands for how much energy is absorbed or released, right? This equation can go both ways, depending on whether something gets hotter or whether something gets colder. M, that's going to stand for your mass, right? Because that's going to play a role. How much stuff do you have to heat up or how much stuff do you have to cool down? That's going to play a role. The C, that's the specific heat value. That's a known value for each substance. That's something that we can measure and you can then use that. Generally, I'm going to give that information to you if I'm asking you to do a problem, because you need that information to solve the problem. Unless, like in tomorrow's lab, I want you to figure out what that specific heat value is. Okay, Mark, go ahead.
At the end?
Yep.
Is that the formula for specific?
That is the unit that goes on specific heat. Okay, so specific heat is going to be a number, but then it's going to have kind of a crazy unit. Okay, all that means, right, Mark, over here, on the left-hand side of this equation, heat's measured in, or heat is energy, so it's measured in joules, right? And that means that on the right-hand side of the equation, this combination of stuff has to cancel everything except joules, because if we have joules on this side, we got to have joules on that side, right? It's got an equation means that one side has to equal the other side. So here, specific heat has a crazy unit, right? But grams is on the bottom, and that cancels with this grams here. Does that make sense? And then delta T, that's, can you guess what delta T is going to stand for?
The difference in time?
Difference, not in time in this case, it's going to be difference in temperature, and that's going to be measured in degrees C, right? So delta T is the temperature change, okay? That triangle is the Greek letter delta. In science and math, we use that to represent the change in something. Here, you do this. Does that help or no?
Yeah.
So, when we are calculating the change in something, we have to know two things. We have to know where did it start and where did it finish. And when we're calculating the change in something, we always go T final minus T initial, where it ends up versus where it began. And that will give us the change in something. Now, it's possible that that change could be a positive number. In what case would something delta T be positive if an object was doing what?
Heating up.
If it was heating up, right? If the final temperature was greater than the initial temperature. But if an object is cooling down, T final is going to be less than T initial, and when you do the math, you'll come up with a negative number. That's okay. It just means that it changed negatively. Okay? Good there? All right. So real quick. All right. Tomorrow, you are going to use an instrument that is called a calorimeter. I'm assuming most of you are familiar with the term calories before. Yes, you've heard that term before. Okay. Calories are a measure of energy. Right? When we talk about calories in terms of food, food is an energy source for you. Right? The amount of calories that are in your food is how much energy you are taking into your body. So a calorimeter is measuring energy. it uses the principle that heat flows from high temperatures to low temperatures until they both reach the same temperature. So that concept of heat, right, of energy flowing from high temperatures to low temperatures until they both reach the same temperature. And when they reach the same temperature, we gave that a name. Do you remember what that name was? Equilibrium. Specifically, what kind of equilibrium in this case? Thermal equilibrium. Now, the important parts, especially for the calorimeter, okay? If heat's flowing from high temperatures to low temperatures, that means that something is gaining heat and something is losing heat. How much heat does something gain versus how much heat does something lose? What has to be true about the amount of energy gained by one thing versus lost by the other thing? It's got to be what? It's got to be equal. Why?
Because the energy is conserved.
Conservation, right? If something's gaining energy, something else has to be losing energy. How much? The same amount. Okay. So, here's how the calorimeter works. Your calorimeter isn't going to look as fancy as this. Your calorimeter is going to be a styrofoam cup with a lid on it, okay? But it works, right? So you want something insulating, right? An insulator that goes around the outside. Why? Because we want to focus on the changes in temperature inside here and not energy from the outside. So we have to keep energy from getting inside of here, right? So generally you fill your calorimeter with water. Why? Well, it's easy to get, and we know the specific heat value. And it's a pretty high specific heat value, so you can put something really hot in it, and it won't heat up all that much. So that's what you're going to do tomorrow. You're going to put some water in your calorimeter. And then you're going to put something hot in it. Here, it says that these things are reacting substances, right? You're not going to put a reaction in there. You're just going to put a hot piece of metal inside of it. But if you put your hot piece of metal in your cold water, what's going to happen to the metal? It's going to cool down. But as it cools down, what's going to happen to the water? It's going to heat up until they're both the same, right? So, right, this reaction releases energy. Your hot thing is going to release energy. And where's that energy going to go? It's going to go into the water. So energy is going to be absorbed by the water. How much? Exactly the same. Why? Energy conservation. Okay. So if we can monitor the temperature change of this water, and we know its specific heat value, we can calculate how much energy it has gained. And if we know how much energy the water has gained, what else do we know?
How much energy the metal's lost?
How much energy the metal loses. Okay. Insulation on the outside, because we want to focus just on the transfer of energy inside the calorimeter, not on any energy from the outside. Good there? And even though we've said it a couple of times already, right? The heat released by the hot object needs to be equal to the heat absorbed by the cold object. So however much heat the water gains has to be the same as the heat that the metal loses. Why? Conservation. Good there? You okay with that? All right. Tomorrow, what we'll do, we will do a couple those example problems down at the bottom of that, down at the bottom of the outline. We'll do those problems at the beginning of class just to give some examples. Then we'll go into the lab, and you'll take your measurements and then do your calculations based on those measurements that you've taken. Good there? Okay. This is the last new bit of information that is in this unit. So at this point, you should be able to at least talk about everything on the objective sheet You know, if you have questions or whatever, tomorrow would be a good day after the lab to ask those questions.